So, we have discussed about the Kohn-Sham DFT. We have discussed what is an LDA, what is an GGA, what is a meta GGA, what is hybrid, what is range separation. Now, we have to see one few common problems of the DFT, and one of the most common problem of the DFT is its inability to describe dispersion like effects. So, one of the serious shortcoming of standard DFTs is the inability to describe the dispersion forces, which are often important in weak interactions. So, many functionals provides a purely repulsive interaction between rare gas atoms or very weakly bonded dimers, and these weak interactions are very important, because remember, in DNA the double helix are stable due to this weak interaction. Protein folding depends upon weak interactions. So, some of the DFT functional totally gives any binding, it gives a repulsive interaction, while other describes a weak stabilizing interaction, but fail to have the correct long range behavior. So, this is actually a problem of DFT. So, Stefan Grimme has proposed a correction to include dispersion by additive empirical terms, much like the van der Waals energy term in the force field methods. So, force field methods, this terms comes ad hoc. We have not still discussed about force field method, we are going to discuss it later in the course. So, this is the form of the dispersion correction used, where there is a parameterized form, and this depends upon which of these functions are used, it is 6, 8 or 10. So, the simplest model, it only have an r to the power minus 6 dependent terms. So, the 6 will come here, or this can be, and this is also a damping function, and we can also include higher order of dispersions into this, and this can be added simply to standard functions using D3 and D4. Remember, MP2, couple cluster, any wave function based method or Hartree-Fock has no problem in describing dispersion. So, this is a particular failure of the DFT kind of method. So, if you are doing an optimization or calculating weak interactions or calculating energy differences, it is always a good idea to use the D3, or the modern variant of it is D4 correction. There is almost negligible computation cost over the standard DFT functional, and these are well parameterized, almost black box to use. So, you should use it for any of the DFT functionals available. To see how important is the dispersion, let us calculate the energy of the diargon. So, energy of the two isolated argon atoms at interatomic distance at 3.6 to 6.4. When I calculate binding energy, it essentially means that I have to calculate it with respect to the two isolated atoms at infinite distance. So, that means I can calculate one argon atom and multiply it twice, and if I calculate the binding energy, then I will find out how much is the binding energy which is coming. You can also plot the normal energy, does not really matter, but to calculate that, what you need to do is to do potential energy scan. That means I have to change the distances, and at each distance I need to calculate the energy and then plot it to get some kind of a curve. Now, one of the major problem of doing this kind of calculation is that you have to do this calculation repetitively at each geometry. So, it can be error prone. So, you need to automate this. We will discuss more about surface scan in the next week lecture, when we will talk about geometry optimization and potential energy surface. But to give you a quick hack, you can actually perform the calculation like this, where R describes your parameters, like I want to start from 3.2, I want to go to 6.4, and like with 9 increments at 0.4 distance. Basically, if I divide it, I will get an increment at 0.4, and this is how you should give the geometry. So, this is argon, and this is the coordinate which is changing, what is given in R. So, what you will do is that you will start at 3.2 and take step of 0.4 and go to 6.4. So, this calculation we should do, and then we can plot the surface with respect to the bond length, and then see how the surfaces actually looks like, and how the DFT behaves with and without the D3 correction. So, let us do that. Let us take this one. Let us create an input file. Okay, this should have been I do not know why I have written def to j, it should have been Rij cos x. Even if you do not give, it will not matter. The opt keyword is also redundant. You don't really need to give the opt keyword here. Um, and the other thing is that why I am using def to SVP. I have always told that the wave function based methods requires really large basis set. Then why the hell I am using def to SVP? Because the CCSD parentheticity calculation can be very expensive. I want to avoid that. So that's why I am using def to SVP, because anyway I am not going to calculate the qualitatively correct binding energy, so it should not be matter. So in that case, that's why I am using def to SVP, and don't forget the exclamation mark. So let me save it as scan cc for couple cluster dot inp and let me run the calculation. This calculation may take a long time. So because it will take a long time, so let us look something interesting which I thought that I should discuss. Let's go to the output file of CH3 minus Hartree Fock. This is not here. I can go and open it. I hope this scan file has been run properly. It seems to have run, okay. But before going that, I want to discuss this one, is CH3M Hartree Fock. Yes, this is my output file. So methane has 10 electrons. When I have CH3 minus, it also has 10 electron. And if I look at my orbitals, you will see here is that the last orbital is very weakly bound, and this essentially means that if I put the electron here, this is not very stable. So because I am using a smaller basis set, the def to QZ PPP, because it does not have any diffuse function, so it still may be giving me a bound energy. What can happen is that if I use a very diffuse function, so this orbital energy may come to 0. And this, if it comes to 0, that means this electron will auto ionize. So when you are dealing with anion, you have to be really careful. If your anion state is not bound, then doing calculation on them can be problematic thing, because in that case, in presence of very diffuse wave function, the electron will just fly away. So my wave function is no longer square integrable. So to treat that kind of system, you need to be really careful while doing any calculation. So after pointing out, let's now go back to my scan, and let me start from the beginning, from the top actually. So this is what it happens. It's take the trajectory step. So from 3.2, it's running couple cluster calculation, Hartree Fock, do the integral transformation, do CCSD parenthesis T, do the property calculation, and then go to the step 2, 3.6. So it's automatically changing, and at the end it's actually plots the bond length versus energy, and it's actually fit a potential energy surface to give you the lowest possible distance, what is the minimum energy, and it says that at 3.7157 angstrom the minima is. You can go and check it in the literature what should be the correct value. So this is what I have got. If you run here it will be there will be a lot of these trajectory files. So, trajectory at the SCF level, trajectory at the MDCI level. So, this if I open it with notepad maybe. So, this actually contains the bond length versus the energy. Remember, these are the energy of the Ar2 dimer. So, let me copy it. This is my sheet 1, maybe I should open another sheet for the potential energy, and here while pasting, make sure that you use the text import wizard, because if you just paste it like this, let me show you, this will not come in a proper format. So, it is a good idea to use the text import wizard. So, the first line often get problematic, and finish it and then I will clean it up. Okay, I get it. Cut and paste it. Okay, let me write, insert another row. This is bond length, and this is CCSD parenthesis D. So, now I have to calculate the energy of the argon atom, and that we can do by just maybe modifying this file. So, basically it is, let me write it as ARCC dot INP and from the ARCC.INP I do not need this parameter here. I only need one argon atom now. I can calculate the energy as twice. So, let me save it. So, what I can do here, I can copy the bond length maybe here. And this is CCSD parenthesis T. This is my single point, finally single point energy of the Ar2 atom. So, let me copy it and then I go here. So, this is the binding energy will be energy of the Ar2 system minus twice let me put the levels properly, CCSDT, and this is bond length. So, here you see that there is a small amount of binding observed here. If you look at this file carefully, the scan cc.out, you see that after this one is calculated, after this energy as different point is calculated, a polynomial is fitted, and this polynomial gives you the minimum, which is find out at 3.8378 angstrom. And if we plot this one, can come to this one, go to more line and scattered plot. I think this is the one I wanted. So there is at least a binding. The binding is not very low because the basis set is not big enough, only triple zeta. Now let us see how the DFT perform for this one. So I can just take my previous input files, so the scan cc.inp, and of course I will check with b3lib. I could have used some other DFT functions also, but b3lib should be fine. I will save this one as scans b3lib. And let me change the ccsd parenthesis t to b3lib and also write rij cos x. I hope with this one the calculation will be slightly faster. And let me also prepare by this time the energy of the individual AR atom in b3lib. Not cc. The calculation is still running. Okay, I think now it's done. So before opening the file, I write ARB. I also run the individual one. By the time it runs, let me open at least the scan output file. So here also it finds actually a minima, but the minima is very far, and when we will plot you will see that is it a real minima or not. So let us go to the trajectory file from where I can copy the this is not needed. So I'll put it here somewhere first. I'll go to paste, text import wizard, next, finish. So I can just copy this one. And I think now the other file, the individual AR for B3 leaf has been done. So I go towards the end. I take the, I think we have by mistake we have done a calculation which is not, because I can see MDCI, so that means it has done a couple cluster. Yes, we have not changed it to B3 leaf, but we can quickly do that. And Rij cos x. Now I save it. So now I believe it's done. So here is the final single point energy. So the same strategy. In this case, almost at nowhere you see a negative energy, and this is actually quite surprising. Here at least you have seen quite good binding. So let me write it as B3 lip and then we can plot it. More charts. So now you see here it never goes below 0. So there is no binding, whereas in the case of couple cluster there was binding. So dispersion is actually particularly a problem in case of normal B3 lip. Let us now see what happens when we add the dispersion correction. So I can start with the simple B3 lip only. I just need to write one single keyword, that is D3, and once we write that I can save it now as scan B3 lip D3. D3 is for dispersion correction by Grimme, and that's the third variant. There is also a D4, you can also use this one. Scan B3 lip dot INP. So let me run it now quickly. Orca scan B3 lip D3 dot INP. Scan B3 lip D3 dot out. So let it get run. By that time, let me prepare the input file for the individual one. D3 dot INP. Just need to put the keyword D3. Save. These data are no longer required. For the time being, I don't need the graph also because I will plot a new one. And this one I will call it as B3 lip D3. So, it is done now. Just want to quickly show you what happens in D3 is that after your DFT energy has been calculated, this is a dispersion correction which is calculated using a force field like formula, and this is added to the DFT energy calculated via quantum chemistry calculation. So, this is what happens in the D3. So, we will run the single point job. So, let me put this one. Okay, the interesting thing maybe I should have looked at is at the end to see after inclusion of D3 what happened to the minimum geometry. Remember, it was more than 5 when we did not had this one. Here also it comes 5. So, in terms of only the geometry, almost nothing actually happens in terms of finding out the minima, but the question is that is it giving binding. So, let me now get the energy. Oh no, I want to open the trajectory file where I can plot the energies. Go to the Excel file, the text import wizard, next, finish. So, maybe I should not have repeated the ARB3LIB-D3 job because it is a single atom. So, there cannot be any dispersion, and if you go towards the end, you will see that the dispersion correction is actually 0 because it is a single atom. So, this is the final energy. It is minus twice of the energy of the 2 argon atoms, and at least here you see there is some binding which was not there. You can see values in negative here. So, if I now plot everything together, line plots, now you see this one. The blue one is couple cluster, the gray one is actually the DFT D3 values, and the yellow one or maybe the orange one, saffron one, is actually the B3LIB. So, in case of only B3LIB, there is no dispersion is there. So, it does not give any binding, whereas when you add the dispersion, this leads to binding in the case of argon dimer, and you can try it for any other dimeric system also, where you will see that the normal functionals does not give you any binding or give you a wrong long range behavior. The moment you include the dispersion, that is generally gets corrected.